In this lecture, I'm going to discuss the method of ordinary least squares, and we will see how to find the formulas to calculate the estimators using this method. Before we proceed further, let's make sure that you are clear with the notations that I'm going to use. So according to the notations that I am using, beta 1 and beta 2 are population parameters. This is intercept and this is slope. These two are population parameters, and UI is the population error term, and their sample counterparts are B1, B2 and EI. So B1 is the estimator of beta 1 and B2 is the estimator of beta 2, and EI denotes sample residuals. Now note that our problem statement is we have to estimate population regression function on the basis of sample regression function. Well, to learn how to do this, let us consider the simplest possible linear regression model. That is the two-variable linear regression model. So let us write a two-variable linear regression model. So yi is equal to b1 plus b2 xi plus ei. So this is a two-variable simple linear regression model in which we have one dependent variable and one independent variable. So this is your dependent variable dv and this is your independent variable iv. Now before I jump to the method of ordinary least squares, let me write a demo sample here. So as you can see, we have only two variables yi and xi. So let us write some values for these two variables. So this is our demo sample, and let's say that y and x can take 5 values, and the values that we have for x are 5,000, 15,000, 25,000, 35,000 and 45,000. And let's say the corresponding y values that we have are 420, 520, 470, 450 and 550. So let's say this is the demo sample that we have. Now let's discuss the method of ordinary least squares. The method of ordinary least squares says that you should choose the value of b1 and b2 in such a way that the residual sum of squares is minimized. And we know that residual sum of squares is equal to summation ei square. So we have to choose b1 and b2 in such a way that this expression summation ei square is minimized. So first of all, let's see what is summation ei square equal to, and then we will see how to minimize it to find the expressions for b1 and b2. Now note that our sample equation is this: yi equal to b1 plus b2 xi plus ei. So from this equation, I can write that ei is equal to yi minus b1 plus b2 xi, where these are your actual y values. So these are actual y values, and this is your predicted or estimated y values. So this is your predicted or estimated y values. So now if this is ei, then we can write that ei square will be the square of this expression. So that means ei square will be yi minus b1 minus b2 xi whole square, and summation ei square will be summation yi minus b1 minus b2 xi whole square. So this is the expression that we have for summation ei square. Now note that we are already given the x and y values in our demo sample. So that means the choice variables that we have in this expression are b1 and b2. Well, this might sound a bit strange to you right now because in elementary calculus courses, we generally take b1 and b2 as constant and x and y as choice variables. But here in this expression and in this system, we have b1 and b2 as choice variables. Now our task is to minimize this function with respect to b1 and b2, and we can use the technique of differential calculus to do this. I'm sure you must be aware of the steps that you have to follow to minimize this function, but just for the sake of completion, let me write down the steps here. So as we have to solve for b1 and b2, let's write down the steps separately. So here let's write the steps for B1 and here let's write the steps for B2. So the first step is that first we have to find the first order condition. So FOC is the abbreviation for first order condition, and we find the first order condition by partially differentiating this expression with respect to B1. Once we have the first order condition, in the second step, we have to put the first order condition equal to 0. And by doing this, we will be able to find the value of B1, which we can call B1 star or B1 OLS. Now, because we have to minimize this function, we have to make sure that the second order condition is also satisfied. So the second order derivative should be greater than 0. This is the condition that we need for minima. So these are the steps for B1. Now we can write the same steps for B2 as well. So for B2, we will have to find the first order condition, which we can find by partially differentiating this expression with respect to B2. And once we have the first order condition, we will put it equal to 0, and this will give us the value of B2, which we can call B2 star or B2 OLS, whatever you want to call it. And then because we are minimizing the expression, we have to make sure that the second order condition is satisfied. That is, the second order derivative is greater than 0. So these are the steps that we have to follow. Now let's proceed with the minimization technique, and let us first work with B1. So we know that summation EI square is summation YI minus B1 minus B2 XI whole square. Now before I differentiate this expression to find the first order condition, I can write it in a more intuitive manner. Note that the demo sample that I have taken, we have 5 values of y and x in that sample. So that means I can write this expression as y1 minus b1 minus b2 x1 square plus y2 minus b1 minus b2 x2 square, and this can go till y5 minus b1 minus b2 x5 square. Now this is your summation EI square. Now let's partially differentiate the summation EI square with respect to B1 to find the values. So this will become twice y1 minus b1 minus b2 x1, and then using chain rule we will have to differentiate this term inside the bracket. So this will become 0 because y1 is a particular number, minus 1 minus 0. Similarly, we can do it for the second expression. For the second expression, we will have twice of y2 minus b1 minus b2 x2, and then using chain rule, we will have 0 minus 1 minus 0, and so on. And for the fifth expression, we can write twice of y5 minus b1 minus b2 x5 multiplied by 0 minus 1 minus 0. So this becomes, the first expression is 2 multiplied by minus 1. So this is minus 2 multiplied by y1 minus b1 minus b2 x1. Similarly, the second expression could be plus minus 2, let's put a bracket here as well, y2 minus b1 minus b2 x2, and so on till the last term. So plus minus 2 y5 minus b1 minus b2 x5. Now I can just write this expression in a short form. So have a look at this expression. I can write this expression as minus 2. So I can take minus 2 common from everywhere. And then it could be written as summation yi minus b1 minus b2 xi, where your I varies from 1 to 5 in this case because n is equal to 5 here. So this is your first order condition. This is what you get when you differentiate summation EI square with respect to B1. Now note that if you are comfortable with calculus, then you don't have to do these many steps to find this first order condition. You could have directly written from here that if you differentiate this expression with respect to B1, from directly you could have written that this will be equal to twice of summation yi minus b1 minus b2 xi, and then using chain rule you would have got minus 1 here. So this is the same thing that you are getting here, but if you are comfortable with calculus, this is a shortest way to do this. And if working with summation sign is something that troubles you, then you can think of it in this manner. Okay, so this is the first order condition that we have. Now note that there is one more method that you can follow to find the first order condition and then work with it. But I will deliberately not show that method in this lecture. I will show that method in the next lecture, and those of you who find that method comfortable can work with that method. For now, let's work with this first order condition. So this is the first order condition that we have. Now we have to put this first order condition equal to 0 to find the expression for b1. So if we put this equal to 0, we get minus 2 summation yi minus b1 minus b2 xi equal to 0. Well, I'm not going to write this I going from 1 to 5 again and again. I hope that is understood here. So this is equal to summation yi minus b1 minus b2 xi 0 divided by minus 2. So this right side is 0 only. And we get summation yi minus n b1 minus b2 summation xi equal to 0. Now note that you understand this well. So I have put a summation sign here with y, a n here, and a summation sign here. See, I have put a summation sign with y and x because y and x are taking 5 values in the demo sample. If you recall, y was taking these 5 values in the demo sample: 420, 520, 470, 450 and 550. So these were the 5 values that y was taking in the demo sample. So summation yi means that I'm taking the sum of all these 5 values. And I have put a n with b1 because b1 is a constant here given this demo sample. Make sure you understand this well. So what I'm trying to say is that when you have a particular sample given, there is only one particular value of b1 and b2 which will minimize the residual sum of squares. So that means given a sample, your b1 is a constant and your b2 is also a constant, and we do not put a summation sign on constant whenever we have a constant, and if there is a summation sign, we replace it with n. And in this case, n is equal to 5, but deliberately I'm not putting 5 here because we are solving it for the general case. So now this is what we have. So this implies that summation yi minus b2 summation xi is equal to n b1. And this implies that b1 is equal to summation yi divided by n minus b2 summation xi divided by n. So this implies that b1 is equal to y bar, which is the mean of actual y values, minus b2 multiplied by x bar, which is the mean of x values. So this is the mean of actual y values, mean of actual y values, and this x bar is the mean of x values. So this is the final formula that we get to calculate b1, and because this is the final expression, you can also call it b1 star, or you can also write b1 OLS. Also observe one thing here, that to find the value of b1 you need y bar, x bar and b2. You can easily find the value of y bar and x bar from the sample that would be given to you. But before you could find the value of b1, you will first have to find the value of b2, and we will see how to find the value of b2 in the next lecture. So till now we have completed the step number 1 and the step number 2, which were to find the first order condition and to put the first order condition equal to 0 to find the value of b1. Now let's proceed to step number 3. In step number 3, we have to show that the second order condition is also satisfied. So basically we have to show that the second order derivative is greater than 0. Now, if you recall, this is the first order derivative that we got when we partially differentiated summation ei square with respect to b1. So we got that this is equal to minus 2 summation yi minus b1 minus b2 xi. Now, before I differentiate this expression with respect to b1, I can write that this is equal to minus 2 summation yi minus n b1 minus b2 summation xi. So this is how I'm writing the first order derivative. Now I can differentiate this with respect to b1 to find the second order derivative. Now if I differentiate this with respect to b1, we will get that the second order derivative is equal to minus 2, this becomes 0, minus n multiplied by 1 minus 0. So that means this is equal to minus 2 multiplied by minus n, and this is equal to 2n. So the second order derivative is equal to 2 multiplied by n, which is obviously greater than 0 because n is the sample size and the sample size cannot be negative. So because the second order derivative is greater than 0 here, this means that the value of b1 that we get by using this formula will minimize summation ei square. So this is all for this lecture. I will continue with this method of OLS in my next lecture, where we will find the first order condition with respect to B2, and then we will find the formula to calculate B2.